So there's this phenomenon called the Doppler effect, the Doppler shift, and I'm going to show it to you first with sound, and then I'm going to show it to you with light. And the Doppler effect, we couldn't understand the Doppler effect until we understood about different wavelengths of light, or different wavelengths of energy. So the Doppler effect looks like this, kind of from left to right. The first little, again, first with sound. The first one is a train is stationary, and to kind of set up the scenario, okay, it's stationary and it's got two observers. Okay, observer over here and observer over here. And now here the train is moving this way. Okay, by the way, so it's stationary, I guess I should say, and can you kind of see those rings? Okay, that's like the sound it's emitting in all directions, including the guy over there and the guy over there. Okay, so they hear it, okay, kind of the frequency, the tone that they hear it is the same. But here's the deal. We're going to set that train in motion, and the person who is on the side of the train where the train is going actually hears the pitch go up. You can almost kind of see the waves being compressed, shortened. Okay, greater frequency, a higher pitch. These over here is going to have their frequency lessened. Okay, the wavelength lengthened, and the pitch is going to go down. Okay, so he sees what we call a blue shift. The direction where the motion's occurring, and he sees a red shift. Actually, the pitch go down. Okay, it's the Doppler effect. Now, aside from this, actually, we've all experienced the Doppler effect with regard to sound. If you have a car that's approaching you and you kind of hear it, okay, that again is the pitch coming from that vehicle. We have a red shift and we have a blue shift and then a red shift. Okay, so now with regard to light sources. Okay, notice the dude in the green hat. I love the dude in the green hat. Okay, so not shown stationary, but here is a light bulb, okay, and this light bulb is going this way, okay? So again, the light bulb is going this way, and so visually, those energies in all wavelengths, but the ones that guy's going to see with his eyes, actually they are going to be shortened. If moving fast enough, he is actually going to see all wavelengths a little bit shorter than the light bulb is emitting. Over there, where the light bulb is leaving, he is going to see actually a red shift. All the colors are going to be a little bit redder. Okay, the wavelength of color is all going to be a little bit longer. Okay, so blue shift, red shift. Towards the moving objects moving towards you, the moving objects moving away from you. So honestly, in Unit 1, we talked about an expanding universe, and we said that Hubble actually looked at galaxies, and in general, all galaxies are moving away from us, and he actually could even clock how fast they're moving. The farther the galaxy, the faster it is receding from us. He used redshift to tell that. So I like this. See what you think. So kind of the first line up there is our library sample. Okay, this would be lines that come from an object that is, these are emission lines, right? That is not moving. Notice that all three lines are shifted here a little bit to the longer wavelength, and then call this A, B, and C. Let's call this L for library, A and B, okay? So can you see where how do I say this? Like here, this is all shifted, okay? Okay, it's shifted towards the red region, shifted towards longer wavelength. Thus, object 2 is moving away from us. Actually, you can see more of an effect in object 2 than object 1, so it's moving away faster. So we'll kind of clear those and look to a couple samples where we see a blue shift instead of a red shift. So can you see where, looking at, this is my favorite one, look at this actually, okay? This first line, because the object's moving towards us, actually had a blue shift clear over here. Okay, then you kind of see those three lines. So object 4 is moving towards us faster than object 3. Pretty cool. Well, the Doppler effect only works if an object is in movement. An object's motion is what we call in the line of sight of us. Okay, that's called radial motion. Side-to-side motion is called proper motion. Okay, and so I'm going to kind of show you some examples. So, for instance, if we have an object that is moving directly away like this or directly towards, we could use the Doppler effect and get a fix on the speed, okay, of that object. We would see a redshift right there in object 1. Okay, radial motion. Now object 2, can you see where it's moving side to side from us? This is called proper motion, and hopefully we'll be able to kind of see it move in the nighttime sky to get proper motion. But we're not going to be able to use the Doppler effect. So I might be able to see its motion, but it won't be from the Doppler effect. And like this last example shows you, usually motion is not entirely radial, nor is it entirely proper. So for instance, but it can be broken down into proper and radial components. So this red line right here is showing you the motion of object 3. Now we can go ahead and use, it's called vectors. Actually, we can break down this motion into 2 movements. We have this radial component and this proper component. So yes, we could use Doppler effect here, but not here. Okay, so that's how that works.